Okay, today we are going to learn about polar forms of complex numbers. So you already know about complex numbers from Algebra 2 and a little bit of what we've done before, but there's also polar forms of complex numbers. In the next couple weeks, you might ask the question, why the heck do we care about this stuff? When I started teaching this, I thought the same thing, and I read somewhere that electrical engineering uses this idea. I think probably like 3 or 4 years ago, I had a student whose dad was an electrical engineer. He asked him that too. And he said, yeah, we do, but we don't use I's, we use J's. So it at least is used in some jobs, if you care to know that or not. There you go. Okay, so first thing that you haven't learned about is that you can graph complex numbers. It's not on an XY coordinate plane, it's on a real and imaginary coordinate plane. So the x axis now becomes the real axis. That's where the real part gets graphed, and the y axis is no longer the y axis, it's the imaginary part. So if you want to get to the point A plus BI, you go to the right A. If it's positive, you go to the left if it's negative, and then up B if it's positive. This point right here would be the point A plus BI. So, example 3 minus 4i. We would go to the right 3, we go down 4, we'd have a point right here. This would be the point 3 minus 4i. Make sure that you actually graph the real part on the x-axis. So this one would be over 1 and down 2. That would be the point 1 minus 2i. Pretty simple, straightforward to graph. You just have to make sure you get the right part in the right spot. Okay, if you look at the title of this slide, it has a lot of different things named by it. It's called the modulus, or the absolute value, or the magnitude. Can't remember where, but either your book or Delta Math calls it the modulus, and then the opposite calls it the magnitude. I've never heard it called the magnitude before, but it's kind of like the magnitude of a vector, so I like that terminology. And then for my math team kids, I also wanted to call it the absolute value, because a lot of times you're asked to find the absolute value of complex numbers. Not a lot of times, but I've seen it done in math team, so I wanted you to know this definition. The reason I also bring that up is I like the definition, because definition of absolute value is its distance from zero. So if this is the it really likes to do that. If this is the point A plus BI, its distance from zero would be this distance right here. So you have this distance A, you have this distance B, which is where the Pythagorean theorem comes in. Z squared equals A squared plus B squared. And this should look familiar just because we've done it now with polars and we've done it with vectors. It's the same Pythagorean theorem that you've seen. So I wanted to make sure that I drew your attention to if they call it the modulus, the absolute value, or the magnitude, all of those mean exactly the same thing. So, for example, if I were asked to find the magnitude of these two complex numbers or absolute value, sometimes you might see it written like this. By the way, since you're allowed to use calculators, your calculator will do it this way if you do type in the absolute value bar. So on your graphing calculator, if you type in the absolute value of -7 plus 24i and you have your calculator in complex mode, it will tell you the answer. But hopefully, because you all know your Pythagorean triples so well, right? -7 squared plus 24 squared. You know that's a Pythagorean triple, and you know that that's 25. Same with this one. It would be 40 squared plus 9 squared, which 9, 40, 41 is a Pythagorean triple. So that is its magnitude or its modulus or its absolute value, whichever term you're being called to at the time. The main reason we're bringing complex numbers back around is for the fact that they can have polar form. This is the stuff that I've heard is true in electrical engineering. So, but I don't know anything at all about electrical engineering, so I can't really show you that part. So the R is that same distance away from the origin, so that R is still the same thing as the modulus or magnitude or absolute value. This right here is called the argument. The angle that you're talking about is called the argument. Or if you want to call it right here, here is your polar form of a complex number, it goes back to the idea of when you graph complex numbers, you go over A and then you go up the B part. And then this point right here is A plus BI. And all of this goes back to what this idea would be. If you graph that imaginary part, the cosine theta is, let's see if I put this as your R, your cosine is equal to A over R and all that other fun stuff. Like all of these things come into play by relating this back to that rectangular. So that when I showed you how to graph these complex numbers originally, that's rectangular graphing. If you wanted to graph them polar wise, you would need that angle and you would need that R, and you could get to that same point A plus BI down here. Now, this down here, let me just change colors for fun. This down here is not in your book, but if you get really tired of writing it, or you may see this in like other books when you go into higher level math, anytime you see the abbreviation cis, so every polar form is in the form r cosine theta plus I sine theta. So why the heck would you want to write cosine theta plus I sine theta over and over and over again? Some older books abbreviate it cis for cosine plus I sine. So if you were doing your homework and you wanted to leave it that way, you could. But your book leaves it as cosine theta plus I sine theta. So does Delta Math. But it has that form for you, so you don't need to worry about getting that in the right form. Okay, so -1 minus I. Just to wrap your brain, now we'll stay with blue for a little bit. We're going down, or to the left 1 and down 1. So here is your point. So make sure when you're doing this that your angle to get to that point is a third quadrant angle. Okay, so to find your R, you would do the square root of -1 squared plus -1 squared. That is the square root of 2, which should make sense. It is an isosceles triangle, oh, and it's a 45, 45, 90, so it's square root of 2. To do tangent, to find what's called the argument, you would do -1 over -1, which is 1. Where does the tangent equal 1? Well, in the third quadrant, the tangent equals 1 at 5 pi over 4. I know some of you have been using your calculator, so if you were to do that, you would probably get an angle like 45 degrees, but you have to get your angle in the correct quadrant in order for this to be true. So in order to write this, you would write square root of 2. You may see the square root of 2 distributed in, but cosine of 5 pi over 4 plus I sine 5 pi over 4. This would be the polar form of that complex number. It gets you to the same place in polar form. Okay, 4 square root of 3 plus 4i. That is in the first quadrant. It's over here. First quadrant. I usually like to draw that first just so that I get my angle correct. And in case I forget how to find r, that will help me find r. 4 square root of 3 squared plus 4 squared. So let's see. This should be a 30, 60, 90, so I should not be working too hard to find this. That should be 8, right? And then tangent of theta equals b over a. So our theta is, where does the tangent equal 1 over square root of 3? If you could see me right now, I'm doing the hand jive, and I see that it's pi over 6. So this would be 8 cosine of pi over 6 plus I sine pi over 6. You can see how annoying it might be to keep writing that same thing over and over again. So you might see, or you might want to abbreviate it, 8 cis pi over 6. Now you get to hear my dog barking. Okay, I'm going to leave this video at this point right now so that, yeah, to stop. And then we'll learn about the next one.